Good day, welcome back. Today, let's check stress transformation from strength of material and structures. Stress transformation, we're going to talk about what we call the plane stresses. So here, what's going to happen is that we're going to consider an element. An element, we're just referring to a point of the material in consideration. So maybe let's say you have a rod like this, then this rod will be under these forces, and these forces obviously will result with stresses in this material. So we're just going to consider a certain point or a certain particle or a certain piece of this material. So that piece or particle of this material, we're going to call it an element. So this is the element. So from this element, we're going to have, this is the element. So from this element, we're going to have what we call X phase and the Y phase or planes. So this side, we're going to call it X plane, and then this side, we're going to call it the Y plane. So this is the 3D, but in 2D, you'll have something like this. You will have this part here, which represent this. Then this one, we're going to call it Y phase. Then this side, we're going to call it X phase. When you check it from the front view, you'll only see the line. So this line, we're going to call it X phase. So we're going to use the same direction from mathematics. Where is it? So this direction or this horizontal direction, we're going to call it X. And the Y direction, we're going to call it Y. So this plane, we're going to call it X plane, even though that it's vertical like this. We're going to call it X plane. Why are we calling it X plane? Is because this plane is normal to this XX, to this X direction. Remember, this vertical plane is perpendicular. It forms 90 degrees with this X direction. So because this plane, it's normal to this X direction, that's why we call this thing X plane. So the same thing with this one, this plane here. Remember, this is the Y direction. So because this plane, it's normal, it forms 90 degrees with this Y direction. Because it forms 90 degrees with the Y direction, or is normal to the Y direction, then we call this thing the Y plane. Right. So we're going to have the forces acting on this plane, Y plane, which is this plane, and then we're going to have the forces or stresses acting on this plane. So these forces, it can be applied manually, like you have this, something like this, and then you pull it like this. Then while you're pulling it like that, then you can have something, you can put something on top of this. You can put a certain object on top of this. So that object is going to apply a downward force like that. Then you'll have a force like that. And those forces or stresses that we're going to talk about, they will be coming from that. Or from the previous sections or lessons, you can have something like this, a vessel. And inside this vessel, you'll have the compressed gas. So if you take an element or a certain part of this material, an element like that, you're going to have an upward force. This material here will be pulled up by this pressure of this vessel. The pressure inside is going to pull this material here will get stretched like that due to this air inside pushing this cylinder in that way, like this and like this. So at the same time, this material is going to stretch like this in this manner due to this force. So if you apply the force on this wall like this, the material of this cylinder is going to get stretched in this direction. So I was just showing you that this stress here and this stress there, they can be from those scenarios, from this scenario or from this scenario. Right. The shear stress, you are going to the shear stress as well. This material is going to experience the shear stress. Where can be that shear stress coming from? The shear stress can be coming from the torque. So if you apply a torque on this rod, rectangular rod, then you are going to have the shear stress. So we're going to have what we call the torsional shear stress. So that shear stress can be given. So, but if it's not given, then you will use this to calculate that shear stress. G, I think over L. Right, so the shear stress, it might not be coming from there. So sometimes the shear stress, it can be from the chimney or the joint itself. Like let's say we have, okay, let's say we have a chimney on top of the roofing. So this is your house. So on top here, we're going to put the chimney like that. So we all hopefully have experienced that if you put something on top, if the planes are like this, what's going to happen there? Like let's say you take your textbook, you tilt it or you put it at an angle like this. Then after that, you take the ruler. You take the ruler on top of this book. What's going to happen is that the ruler is going to slide. So once this ruler starts to slide, then once there is a sliding of surfaces, then it means that there is what we call the shear force. And once there is shear force, that shear force acting over a certain area, that shear force is going to give us the shear stress. So now to join this thing with this roof of yours here, before you join this thing, you have to know the amount of shear force that is going to develop there, the magnitude of the shear force that will develop there. So the magnitude of the shear force that will develop here, to see that there is shear force there, you will see this thing will slide there. So now we need the joint that is going to stop this thing from sliding. So normally the type of joint that you're going to use will depend on the magnitude of this. So remember, we can use glue to join this thing here. We can weld or we can use anything. So, but normally before you decide here, you have to calculate the shear stress that will develop. So now to find the shear stress at this plane, we can use this method that we are going to learn, or this technique that we are going to learn. Right. Let me say, let's say the roof of your house is like this. It's plain like this. So if it's plain like that, then we're going to say that the plane is horizontal. We're going to have the horizontal plane. I remember I said that here we're going to talk about the plane stresses. So if the roof of your house is horizontal, then that roof, let's say this is the plane. Your roof is flat like that. So it means that our plane is horizontal. The plane is going to be like this. So if you take the chimney and then put it here, you take this, you put it here. What's going to happen? This thing will just sit there. There won't be sliding. So the weight of this red thing is going to sit here, and then there won't be any sliding. But if you change the plane of your roof from this to that to this plane, and then you put the chimney on top, what's going to happen? This thing is going to slide. You will see this thing is going to slide. So now we've changed the plane from this to this. So once this chimney, which is represented by this arrow, once it starts to slide, what is that telling you? It's telling you that there is a sliding force. Then when you take that force divided by this area, you're going to have a sliding stress. That sliding stress, I'm talking about this shear stress. It means that once this thing starts to slide, there is what we call the shear. So which is the shear stress. So the shear stress, the magnitude of the shear stress depends on what? It depends on the slope or the plane. So we've seen that when the plane is horizontal, there won't be sliding, there won't be shear stress. I'm just talking about this scenario. It's not always the case. It's not always the case that when the plane is horizontal, it means that the shear stress is no. Like here, the plane can be horizontal, but because of the torque, the shear stress will be there. So here I just want to make a point that as you change the plane, the magnitude, the shear stress gets affected as well. So as if the plane is horizontal, the shear stress will be zero. But once you change the plane, the shear stress will develop. Then the magnitude of the shear stress, the magnitude of the shear stress that will develop here will depend on the angle of this roof or the angle of this plane. So we're going to have different angles or different planes. So as you tilt at the roof, then the shear stress as well will keep on changing. The same thing with the normal stress. The normal stress will get affected by the plane. So like if you have your plane is like this, then we're going to call this thing the normal. This thing, we're going to call it normal stress. Why? Because the direction of the weight of this chimney, this arrow, as I've said, represented this chimney. The weight always acts vertically downward. So if it acts vertically downward, when you check this plane, this two will form 90 degrees. Therefore, we're going to say that this stress is normal to this plane. But once you change the plane or you change the plane of this roof to this, then your plane will be like this. And then when you put that thing on top, the weight of the chimney will still be acting vertically downward, no matter what. So the weight of the chimney will be like this. Now, this stress here, you can't call it normal stress. Why? Because this line together with this, they don't form 90 degrees. So once they don't form 90 degrees like that, then this stress or this force is no longer normal. Therefore, the normal stress will change to this. So we're going to have normal stress in this direction. So you can call this stress and this plane. You can say this stress is normal to this plane. Why? Because they are forming 90 degrees. Right. Even so that the weight of this chimney is not going to change. But this normal stress caused by the weight when the plane is like this is not going to be the same magnitude of this normal stress caused by the very same weight while the plane has changed. Right, let's have a look here. You will see that you are going to have the values for normal stress and shear stress on the Y phase and on the X phase. So I'm talking about these stresses here. And the stress that will act here, we're going to say the stress that acts here, remember we call it stress on the Y phase. The stress that will act here, we call it the stress on the X phase. Right. So as we tell the element, this is the element. I spoke about the element. So this is the element. As we tell this element, or as we change the plane, the normal stress on the X phase and normal stress on the Y phase will change as well. And then the shear stress will change as well. So as you tilt this, as you change the plane. So now we're going to use, or in this chapter, we're going to study, or we're going to see how to find the stresses at different planes. So as we change the element, as we rotate the element, the stresses will change as well. So in other words, we are going to tilt this element by maybe 5 degrees or 10 degrees. Then from there you'll find the stress. Let me go back to this. Normally, in general, what we're going to do here, we're going to have the plane being horizontal like this. And then we find the normal stress and the shear stress at this plane. Then from there, you change the plane from here to here. Then you find the normal stress and the shear stress. You change the plane from here to this. From 5 degrees, from 0 degrees to 5 degrees to maybe 40 degrees. You keep on finding the stresses as you change the plane, as you change the plane, as you change the angle. So you'll have your element being like this. Then you change the angle of this plane to this. You change the angle of this plane to this. As you change the angle of these planes, then the normal stresses and the shear stresses will keep on changing. Uh, right. From here, let's move to the direction of the shear stress and the angle. So on our formulas that we're going to use, we're going to find the value of the shear stress. Uh, in most cases, it's going to be given. But if the shear stress is not given, you can use this formula here. And then the shear stress is going to be written like this, like this. So just know that the first letter from that shear stress is going to represent the plane. So I spoke about the plane. The plane, we're talking about this and this. So the first subscript there, like here, is x. It means that this shear stress is the shear stress on the x plane. So if the first subscript is y, then it means that that shear stress is the stress that is going to act here on this y plane. So the shear stress that is going to act here on this y face, we are going to call it shear stress y. So the shear stress that is going to act on this x plane, we're going to call it shear stress x. So the second subscript, this one, normally the shear stress will have two subscripts. This second one is representing the direction. Like the shear stress on this y plane is acting horizontally like this. Then remember I said that we're going to have the direction, this vertical direction is y, this horizontal direction is x. So meaning that this shear stress on this y plane is acting in this x direction, the horizontal direction. So that's why we're going to have x here. So that's how you will interpret this. So this is the shear stress where on the y face, in which direction? In the horizontal direction, which is x direction. So that's how you interpret this. So the same thing here, we're going to have the shear stress we're going to have the shear stress on the y face. We're going to have the shear stress here on the y face. Sorry, on the x face. This is the x face. So this is the x face. So we're going to have the shear stress on the x face. In which direction? What is the direction of this arrow? This arrow is vertical. So vertical is what? Is y, in the y direction. So while you will have the shear stress on the x face, this is the x face. We're going to have the shear stress acting here. In which direction? In this direction of y. So that's why we're going to name this stress here as x, y. Shear stress on the x face in the y direction. So now this stress sometimes is going to be positive, sometimes it's going to be negative. So the direction will depend on this. We're going to have clockwise and anti-clockwise. Let's check here. If you have something like this, a box or whatever, if you move around this box in this direction, what will be this? This is anti-clockwise. Remember, a watch or a clock moves like this. This is clockwise. But if you move like this, upward, like this around this, you will be moving in an anti-clockwise direction, which is the direction opposite to this. So to determine the direction of the shear stress, you must always check the x phase. Maybe let me write it. Let me write it down. Right, on our formula sheet, you will see we're going to have this stress, shear stress xy. We're not going to have this one. You will never see shear stress yx. You will see shear stress xy. So shear stress xy is this stress on this face. So this one we're not going to use it on our calculation. We will use this one always. We're always going to use shear stress on the x face in vertical direction. So you'll see on your formula sheet, I'm trying to go to the formula sheet. Yeah, you will see here on the formula sheet, this is what I was talking about. Shear stress xy. You will never see yx, xy, xy. So because of this, that's why we're saying that we're always going to use shear stress on the x face. So this statement is talking about that. So we always use direction and shear stress value that is on the x plane. So which is this stress here. So now how to check the direction of this shear stress here? So I've already said that we are going to check this part. And when you check here, you will either find the downward arrow or upward arrow. So sometimes the arrow will be going down, sometimes will be going up. So if it's going up like this, then you'll move upward around this element. So as I've indicated before, so you'll move upward around the element. Then when you move like this, then it means that you will be moving counterclockwise or anti-clockwise. And then we take this counterclockwise or anti-clockwise direction as positive. So we take anti-clockwise as positive. Positive shear stress. So that means on our formulas that I've shown you, you replace the shear stress with a positive value. You will see that at the later stage. So sometimes when you check the given element, uh, the arrow on this x face will be going down. So like if you go down like this around this element, you move like this, what will happen? What is the direction here? The direction is going to be clockwise. This is clockwise movement. So when you move like this, you will be moving clockwise. So clockwise will be taken as negative. Meaning that on that formula, on those formulas that I've shown on the formula sheet, you will replace the shear stress by the negative value. So if you see that from your element, you have the downward arrow on the x face like this, then your shear stress will be negative. Right. So the same value applies with the angle of theta. Uh, the theta will be talking about the angle of this plane. Remember, I said that we are going to rotate this plane, the plane of this element. We are going to change the element from this plane. We rotate it or we tilt it to that. So that angle is going to be the angle will be represented by theta. Right. So the theta as well will either be negative or positive. So how to determine whether the theta is negative or is positive? So you will have a plane like this. So if you take this and rotate it like this, okay, remember our direction. This is y direction. This is x direction. So even if you tilt this thing like that, this will be x, this will be y. So in general, if you have this x line, so normally they will give you the angle. If the angle is above this line, if the plane is above this line, or if your element is rotated and it's like this, the angle of this plane will be measured from here to there. So if the angle of this plane is above this x, above this direction, then we're going to say this is positive. Remember, when you measure from here to there, you will be moving anti-clockwise. So counterclockwise or anti-clockwise direction will be taken as positive for theta. So it's up to you. You can see if the angle is above this x line, or if from here to this black line here, which represent the plane, from this x to this, in which direction are you moving? You will be moving anti-clockwise. So it's either you say measuring the angle anti-clockwise, or you can say if the angle is above this x line, then you will have a positive theta. So sometimes we are going to have, okay, this is the direction, horizontal direction is x. So sometimes you are going to have the angle being measured like this. Theta will be like this. So if theta is below, or this is one, let's say when it's above, then theta is positive. So if theta is below this x, if you are measuring clockwise, remember from here to there, this direction is what is clockwise. This is clockwise. So we can say clockwise direction, or if theta is below the x, what are you going to have? We are going to have the negative theta. The theta will be negative. So that's how you'll determine the direction of the theta. So it's all about in which direction are you rotating this element. So if you have the element like this, it will either you rotate it like this, which is this direction, is going to be positive. So if you take this thing and then you rotate it like this, it's like here you push it like that, in that way it will tend to this. Then you are going to have negative. Right. So you are going to see that as you solve the problem, just keep that in mind. So these directions are very important. Once you miss this direction, it means that your calculations as well will be affected. Right. I will explain some of the things along the way. Let's check this problem here. In a structural element, the stresses at a point in a material is shown in figure 1.2 below. Use stress transformation formulae, those formulas that we've seen on the formula sheet, to calculate the principal stresses acting on the element and the position of the planes in which they occur. Right. What is the principal stress or principal plane? Right. Principal planes is the planes on which the shear stress is zero. Principal stresses act on principal planes. So we are going to rotate this thing. So as you rotate this element, okay, let's say we initially rotate it to this smaller angle. So when you rotate this element like this, the shear stress will no longer be 15. The shear stress maybe will get reduced to 9 MPa. And then this normal stress, remember shear stress is 15. Then it will change from 15 to 9. Then this 30 as well will change from 30 maybe to 20 at this angle. Then as you keep changing the angle or changing the plane from this plane to this plane, the shear stress as well will change from 9 maybe to 2 MPa. And then the normal stress will change from 20 to, I'm just giving an example, to 15 MPa. Then as you tilt it maybe to the bigger angle, to this angle now that shear stress from 9 to 2, the shear stress will be 0. And then maybe the normal stress on the X face will change from 15 to 10 MPa. Now, at this plane, I said that the shear stress is going to be 0. So at this plane where the shear stress is 0, this plane, because when we rotate this element to this plane, the shear stress is going to be 0. So at this plane where the shear stress is 0, this plane we're going to call it the principal plane. The principal plane is the plane on which there is no shear stress. Now, the stress that acts on this plane, where the shear stress is 0, this stress that acts on this plane, remember the stress here equals to the stress here. Don't get surprised. If the stress is 0 here, it means that the stress is 0 here. The shear stress will always be equal. The shear stress here and the shear stress here, they will always be equal. It's just that they will be in opposite direction. I will come to that just now. So the stress, the normal stress that acts on this plane, which has the 0 shear stress, this stress, we're going to call it principal stress. What is principal stress? Principal stress is the stress that acts on principal plane. What is principal plane? Principal plane is the plane at which there is no shear stress. So since there is no shear stress here, or since there is no shear stress here, then this plane, it's a principal plane. Then on this plane, we are finding what? We are finding the stress of 10 MPa. So the stress that acts on the plane where there is no shear stress, that's stress we're going to call it principal stress. And therefore, this 10, it qualifies to be called the principal stress. So remember this 10, I was just giving an example. So now in this question 8.1, we have to calculate the principal stress. We have to calculate the principal stress, not this one that I've just given from my mind. So to calculate the principal stress of this given element, we are going to use this formula. You will get it from your formula sheet. Here's the formula. So I'm writing this formula down. So I've just copied that formula there. Then I'm going to substitute. So all these values, we're going to get them from this element here. One other thing is that for this element to be in a state of equilibrium, it means that when you apply a force or a stress in this direction, to balance this, there must be a force in opposite direction of the same magnitude, or a stress. So that's why this stress from this side, when you apply stress on this side, there will be reaction stress on the other side of the same magnitude. The same thing when you apply or pull a component or anything, for that thing not to be in a state of equilibrium, when you apply a force in this direction, it must react, or there must be a force in opposite direction for this thing to be in a state of equilibrium. So that's why when you have 25 here, you will have the same 25 in opposite direction. So the same thing applies with the shear stress. If there is a shear stress in this direction on the x face, this direction this is still x face on this side, which is clockwise. Remember this direction, this downward here is still clockwise. So if you move down like this, you are still moving clockwise. If you move up like this, you are still moving clockwise. So if there is clockwise shear stress on this x face, for this thing not to rotate, not to turn, for this element not to turn or not to rotate, because if you tilt this thing like that, this thing is going to rotate in a clockwise direction, in an anti-clockwise direction. So to prevent this thing from rotating in that direction, there must be an opposing shear stress in opposite direction. So this is anti-clockwise direction, then there must be what we call complementary shear stress in opposite direction. So to balance this thing not to rotate, for this thing to be in a state of equilibrium. So that's why you have the shear stress in this direction. Remember, this direction is clockwise. This is clockwise on the Y phase. So on the Y phase, you're going to have clockwise shear stress. And then on the X phase, you're going to have anti-clockwise shear stress. So that will always be the case. So we'll have clockwise here, then we'll have anti-clockwise here for this thing to remain in a state of. So remember, I've started with the directions. We said that anti-clockwise is negative. Sorry, anti-clockwise is positive, clockwise is negative. I hope you still remember that. So the same thing with the stresses. We know that with stresses, if you have an arrows going inward like this one of 30, it means that the stress is compressive. So for compressive stress, we're going to use negative. Then if they're moving away from each other like this one of 25, then we're going to have tensile. So for tensile, we use positive. So now we're going to substitute here. Equal to stress X. The stress acting on the X phase, this is X phase, is going to be 30. But we have these arrows going in like that. That means we're going to have what? We're going to have compression. So compression will be negative. Then positive will be tensile. Right. We're going to have negative 30 plus stress acting on the Y phase. This is Y phase is 25, it's tensile. Shear stress where? On the X phase, which is acting in Y direction. So what is the direction of this shear stress? Upward. When you move upward like this, which direction is this? Which direction is this? It's anti-clockwise. Clockwise is this one. So this one is anti-clockwise. So we said that anti-clockwise is going to be positive. That's why we're going to have positive shear stress. This 15 is for shear stress. So we're going to have positive 15 squared. Then you press calculator, you'll have 28 MPa. So remember, we're going to have two planes. We're going to have this plane here and the plane here. So that's why we are going to have two stresses. So from that sketch that I've drawn before, I said that if shear stress is 0, shear stress is 0 here. So the stresses that act here, we're going to call them the principal stresses. So this is principal stress. This is principal stress. We have to find the stresses on both plates. So this one, we don't know whether it's for this or is for this. I will show you how to determine if this stress is for this plane here or is for this plane. I will show you at the later stage. But for now, let's find the another stress on the other plane. We have to find two stresses. So yeah, so the difference between the formulas is just the sign. So this one is positive, this one is negative. So you will get this as principal stress number 2. And since we get negative here, it means that, as I've said, that we don't know whether this one is for this one is for this. We don't know that. I will show you that at the later. But if you get negative here, it means that the stress, let's assume that this one, let's assume that 28 is for here. Then this one, because it's negative, you are going to have compression. So that negative is just mean the compression. Then we're going to have 33.8 MPa. So that is the meaning of this negative. If it was positive, then your arrows, they were gonna be like this, outward. Now, just to check if these things they are right, you can use this. We use this to check whether our answers are correct. So let me write here. So after calculating the stresses, you can always do this. Check. The normal stress on the x-face before rotating the element plus the normal stress on the y-face should be equals to normal stress after rotating the element on the x-face plus normal stress after rotating the element on the y-face, and the principal stresses should be equal as well. So at the moment we don't have these ones, but we have this and this, so we can equate, see if they're equal. Let's just substitute. Normal stress on the x-face before rotation is going to be this one, 30, but it's compressive, so you must put negative. On the y is 25. Normal stress 1 is 28 plus number 2, I mean principal stress number 2. Remember, these are the principal stresses, which is what we've just calculated, negative 33.8. So here you will get negative 5. Pressure calculator, this one minus this one, you'll also get negative 5. So then if they are equal, then it means that you are on the right path. This one is previous question paper. I've just checked the memo as well. Then the answers are correct, but this part here is not right. So just be careful. Right, they didn't ask us to calculate the principal stress only. They've also requested us to calculate the position of the planes on which they occur. In other words, we're looking for the angle on which the principal stresses act. So it's just this angle here. As you can see, this element is rotated. This element here. So we just have to find the angle at which this element will be rotated so that the principal planes can be 28 and negative 33. Or in other words, we are trying to find an angle that as we rotate this element, there will be a certain angle that when we keep rotating this element, the shear stress will be zero at that particular point or at that particular angle. So we're looking for that angle where the shear stress will be zero as we rotate this element. Now, to get that angle, we are going to use this formula. So it's simply the angle of this element here. So to find that angle, we're going to use this formula. Then we have everything. You just have to substitute. We will have 2 multiplied by. Remember, the sign is very important here. If the shear stress is positive, you put positive. If it's negative, it's negative. The same thing, the sign is very important. The normal stress on the x face is compressive. You will have this. Then you find the inverse of this. This is basic mathematics. The inverse, we say 2 right. So on the Mohr cycle, but you are still going there. But maybe you still recall it from N5. So this is the y plane, this is the x plane, or this one can come this side, this one come this side. So on the Mohr cycle, you will remember that this thing, they are separated like this, which is 180 degrees Celsius. So a straight line is 180 degrees Celsius. So because of this, we are going to have 2 angles for principal planes. Remember, we've got 2 planes. We've got this one and this one, which are separated by the angle of 180. Then you can say the first plane will be equal to this, and then the other plane will be equal to 2 theta p equals to 28.6 plus 180. And then this divided by 2, you will get 14.3. I think it's going to be negative. This thing divided by this, it should be negative. So it should be negative. those are those two angles of the principal planes. So someone can simply, we know that on the element, I think I will need more space, but let me just throw it here. On the element, we know that this plane and this plane, they are separated by what? By 90. So if you know this angle, to get this one, you can simply say this one plus 90 degrees. Okay, someone can do it like this. I will show you. Once you get this theta p, to get the other plane angle, you can simply say yeah, so in general, it's going to be always like this. I'm just showing you that if you don't want to take this route, you can find theta p. Remember, 28 is not theta p. 28 equals to 2 theta p. You can find theta p, and after finding theta p to get the other plane angle, you just say 90 plus that plane angle. But just be careful of the sign. If the angle is negative, then you must also put negative. And it will be negative 14.3 plus 90. Right, this angle doesn't matter, it's the same as this angle. Remember, they originate from this. So it's like you have this line, this angle, and this one, corresponding angles equal. So this angle, which is represent the angle at which you've tilted this element, is represented by this angle. So this is that theta p. So the angle from this x to this is theta p. Then if you want to know the angle from here to this y, to this plane here, then it will be theta p plus 90. This angle here is going to be theta p plus this part here plus this angle. This angle here is 90. From here to there is 90. Therefore, the total angle from here to there is going to be theta p plus 90 degrees. So this theta 1 is the angle from here to this normal stress, which is the principal stress in this case. And then this one here is the angle from this x line to this principal stress or to this normal stress. So I'm just showing you this so that you don't memorize this. Don't just cram this. You must understand them. Oh, sorry, but anyway, this one is valid for when we have the positive angle. Positive angle meaning when we have an anti-clockwise. If you rotate this thing in an anti-clockwise direction, that's what we're going to have. But if you rotate it clockwise, which is our case scenario for this problem, then you are going to have your x like this, then you are going to have your element like this. So remember, if you have negative angle, which is what we got, that means the element will be rotated in which direction? Clockwise direction. So the element will be rotated clockwise like this. So this element will get rotated clockwise, which is this. So now if it's rotated like this, this is that principal stress on this plane, on this x-plane. Then we're going to have another principal stress here. So that theta P is going to be this angle or this angle here. It's the same thing. So now that other angle, just this one, is going to be the angle from this to this other plane or to this normal stress here. Remember those stresses, maybe principal stress 1 is this one, principal stress 2 is this one, and this one. So from XX to principal stress 1 is theta P1. From XX to principal stress 2 is theta P2. So now, if this angle here, you can see saving the total angle of 90. This angle is 90 degrees. So if this one, which is theta P, equals to 14.3, then how much will be this angle here? How much will be this one? So this one obviously is going to be 90 minus 14.3. So which is that 75.7. So 75.7 degrees is the angle from this x to this stress, from this x line to that stress. That's x line, you can draw it here. You can draw it anyway. From here to there, it's 75. From here to there is that 14. From here to this normal stress on the x, principal stress on the x face is 14. And from here to there it's 75. So that is for clockwise rotation. Then for anti-clockwise rotation, you'll have this. For clockwise rotation, you'll have this. Anyway, for anti-clockwise direction, we'll have 90 plus theta. 90 plus theta. For clockwise, we'll have 90 minus theta. But we don't have to worry about this. You will can always stick to 90 plus theta. But we must just, since here for clockwise, we will have negative theta. Clockwise, it means that the theta is negative. Then we'll have this. Then we'll have positive by negative. Then we'll have negative theta. So now you have two angles, you have two stresses. So to check which angle goes with principal stress, you are going to use this. So as I've been explaining using this, let me continue with it. What did I say about normal stress? Normal stress is the stress that acts perpendicular to the plane. So this one, if it's acting perpendicular to this, then it's normal stress. 28 is normal stress. But if there is no shear stress, if shear stress is zero on this plane, it means that this stress is also principal stress. So this 28 is going to be normal stress. Why? Because it's acting perpendicular to this. So this 28 is normal stress. But at the same time, this 28 is acting on a plane where the shear stress is zero. So that means that this 28 as well is what? It's principal stress. So I was coming here. I'm coming here. The normal stress equals to principal stress. So to check which angle goes with principal stress, we're going to use this formula. And remember, this formula is for calculating the normal stress after rotating the element. So don't get surprised that now, why are we using this normal stress formula to calculate principal stress? Or why am I equating these two? The normal stress and the principal stress is because of that reason that I've mentioned. So always, you can always do this. You calculate principal stresses, but when you want to check which angle goes with which stress, then you come to this formula of normal stress. You will get this formula from the formula sheet. Here's the formula sheet. Here's the formula sheet. Good. So that's how you check. So meaning that this angle of 14.3 goes with this principal stress of 33. Remember the principal stress, we've got two values, 28 and 30, negative 33.8. So meaning that this angle of 14.3 goes with the stress of 33. Or the direction of this stress, 33.8, is this angle of negative 14. So what does this mean? It means that this is the reference, this is the x. It means that this principal stress 1, which would be equals to stress on the x phase, normal stress on the x phase. This one is going to be negative 33.8 MPa. Yeah, but that negative, it means compression. We have to write an arrow like this. Compression, and the angle is going to be 14.3. Then from this, on this one, is going to be that angle of 75.7 degrees. Then it's going to correspond with that other stress. It's going to correspond with that other stress, which is 28.8. 73 goes with 28.8 MPa. So that's what they wanted. And this one always theta p. The theta p1, this one, will always go with stress x. This one will always go with stress x. Yeah, that's why here I've used the formula for stress x, normal stress on the x face. Remember, if it's normal stress on the y face, the formula will change. We've got two formulas, remember, you'll see them on the formula sheet. So this theta p, this one would always go with that formula. So if you use this angle, then you must use that formula. Then you must use plus. Then that means this is going to give you the stress where on this. Right, now let's verify our answers using the Mohr's cycle. So now we are done with question 8.1. So now let's go to 8.2, draw Mohr's cycle to verify your answers. Right, you take a ruler, you draw your, can call it Cartesian plane. Yeah, from there you mark your 1 centimeter each. Remember, 1 centimeter equals to 5 MPa. So you mark. I hope you can see those red dots there. One centimeter equals to 5 MPa. Right, so this is the graphical method. Uh, we're going to use a cycle. From the cycle, all stresses at different planes can be determined. You keep on changing the plane. So when you keep on changing the plane, you can read all those stresses from this cycle that we are going to use now. So uh, this one maybe uh, they prefer this method during those old times where these scientific calculators maybe they were not developed, or these computer softwares they were not developed by that time. So without the calculator, whatever, you can use this to analyze the stresses on the plates as they are changing. Right. We're going to differ a bit with mathematics. We know that on the Cartesian plane of mathematics, this horizontal line is normal. So the horizontal line here, it represents the normal stresses. The vertical line represents the shear stresses. Uh, but from mathematics, we used to take this part to be negative, then the top one positive. So here we're going to differ. The negative is going to be above. As you can see, negative stresses will be above, then positive stresses will be below. So this vertical line represents the shear stress. So first of all, we can find the center of the circle that we're going to try to draw. So the center of the circle will be given by this formula. C equals to stress, normal stress on X face, normal stress on Y face, divided by 2. You can also call this thing an average stress, average stress. So from our element, normal stress on the X face is -30 because of that compression. On the Y face is 25. Then you will have -30 plus 25 divided by 2. -2.5. So once we find your center, you can come here. You check your 2.5. 2.5 is going to be somewhere here in between, or maybe I can use my ruler as well. I will use my ruler to check that 2.5. Yeah, it will be here. Right, so that will be the center of our cycle. Now let's mark our normal stresses. We've got -30, -30, and we've got is it 25? 25. Here we go. But let's go to our stress element. On X face, let me erase this. on X phase, we're going to have two stresses, which is this 30 together with this. So we're going to have negative 30 because of this compression. Then we're going to have this. This is anti-clockwise shear stress. It's 15. Is it positive or negative? Yeah, it's going to be positive. Anti-clockwise is positive. Then this is going to be your coordinate. Positive 30, negative 30 and positive 15. So this is going to be your first coordinate. So you check negative 30, is already this one here. Then shear stress, you check positive 15. Then where they meet is going to be a point. Where they meet is going to be a point. So positive 15 is underneath. Shear stress, positive is underneath. Remember, the shear stress can be positive, can be negative. So this positive is because of that anti-clockwise movement or rotation. So anti-clockwise is positive for shear stress. I've started with that part. It's not visible. Let me change. Yeah, positive 15 and 30. Okay, this will be your first point. And the other one, you go to the Y face. When you come to the Y face, you will have two stresses. You have the normal stress. You have normal stress there, which is 25 is tensile, positive. Shear stress, here's your shear stress, this black line, this one. So it's going in that direction. So when you move like this around this element, that is clockwise. Then we said that clockwise is what is negative. Then you are going to have negative 15 MPa. So shear stress will be the same. Shear stress here, here, here will be 15. It's just that they differ with direction. So at some point it will be negative, at some point it will be positive. But normal stress, you can see they don't have to be the same, 25 and 30. But shear stress will be the same. Right, now we go to our Cartesian plane, or we have to plot or find positive 25, which is this one here, and negative 15. So negative is this side. So let's start with this 25. 25 and negative 15. Remember the center of our circle will be here. So here you will have shear stress, 25, then negative 15 as shear stress. So this is normal stress, this is shear stress. The same thing applies on this side. Negative 30 and positive 15. Normal stress and shear stress. Right, but there is no need for this. You don't have to put them, you can remove them. And even these constructions lines, you can remove them now or at a later stage. Make sure that you make them light. These are the constructions lines. Remember, we don't want this. We wanted to this point, this dot here. We don't want this. So as long as we've marked our points, we can remove them. So, but during construction, make them as light as possible. So from here, you will need the compass. Here's your compass. This is your center. You put this edge here at the center. This is where there is that 2.5. Then from there, you're going to take this, stretch it up until it touches this dot here. So it either it touches this one dot here or this one. It should be the same thing. So it should be the same thing. Oh, by observing these distances, I'm not getting the same thing. Here is 5.6, 5.5, here it's 7.1. No. Sorry for that. I did mistake. Remember, C is negative 2.5. Check here. The center is negative 2.5. So this is positive 2.5. It must be negative 2.5, not positive. So negative 2.5, it will be this side. It will be this side. Right, so 2.5 will be here. So you put it there, then you stretch your compass until it touches one of these dots. 6.4, it doesn't matter, you touch this side or this side. So yeah, it's almost there. 6.3, even here it's almost 6.3. Good. Right after this, you draw a cycle. So you draw a cycle, then you'll have this. Passing, that means my mark were not that great. It was supposed to pass here. Uh, yeah, but it's fine since it's a graphical method. You are going to use tolerance. But it was supposed to pass on this dot. Even here, it was supposed to pass on that dot. But it's fine. Let's continue. After this, we're going to have the problem with the shear stress. Then I have to increase this side of the shear stress. Yeah, so guys, if this thing is like this, any point, a point on the cycle represents the state of stress on the corresponding phase of the element. So this point here, which is going to have this plane like this. If you want to know the stress values at this plane, then you just have to measure from here, from the origin to there, about 28. Then that will be the normal stress. This will be the normal stress, 28. Shear stress, you just have to measure from vertical, from here to there, which is maybe 9. So if you want to find the stress at this point, is going to represent the stress on that element when it's tilted or when it's at this plane, when it's rotated to this angle. So as I've said that any point on the cycle represents the state of stress on a corresponding phase of the element. So you can find stress at different planes. If you want stress at this plane, you just have to mark here on this cycle or trigger the vertical line. The corresponding stress, normal stress will be 15, shear stress will be 20, maybe 24, just like that. So as we know from N5, the rotation angle on Mohr'S cycle is double to the angle on the stress element in the same direction. So I don't know if we are going to apply that. Yeah, we are going to apply that later. But just recall that when you have an element like this faces this one and this one. What is the angle between the two? Is 90 degrees. On the element, these planes and this one, this y plane and this x plane on the element, they are separated by a 90 degrees angle. This x face and this one, which is the y face, They are separated by an angle of 90 degrees. This is the element. Now, let's check here. From the center to normal stress of 25. From here to there. Remember, 25 is what? 25 is normal stress on the Y face. And from here to there to negative 30. Remember, negative 30 is normal stress on the X face. So actually, maybe in the next step here, you join this. Let's join this. Join these dots. You have to pass through that center there. So draw a line. Good. So what I was trying to say is that when you check from your element that 30 is acting on the X face, the negative 30. That's why I'm going to say from here to the negative 30. Remember, this is 30. The negative 30 is going to be the X face. Then from here to 25, 25 is normal stress on the Y face. Now, when you check these faces on the Mohr'S cycle, they are separated by an angle of 180. Then on the element, they are separated by an angle of 90. So because of that, it means that from this element to the Mohr'S cycle, the angles will multiply by 2. So if they give you angle that the angle on this element is 30, when you come to this Mohr'S cycle, you take that angle multiplied by 2. So as you can see, this face is here, the X face and the Y face, they are separated by 90 degrees, but when it comes here, they are separated by 180. So it's the same thing with the angles. So sometimes you're going to measure, they are going to say find the angle of the element. But to find that angle on the element, we have to get it from the Mohr'S cycle. So from Mohr'S cycle, the angle that we get here from the Mohr'S cycle, when you convert that angle to this, to the element, you take that angle from Mohr'S cycle, you divide it by 2. So from Mohr'S cycle to element, we divide the angle by 2. But from the element to Mohr'S cycle, we multiply the angle by 2. So just remember that. So now the principal stress, which is what we have to find. Remember the principal stress? We'll find the principal stress at the point where there is no shear stress. At this point, there is shear stress. If you want to know the shear stress at this point, you measure the vertical line from here to there. So it's going to be 15. At this point, shear stress is 15. At this point, shear stress is there. If you want to know the shear stress, you measure from here to there, the vertical line. It's going to correspond with 8. So shear stress is 8 there. There is shear stress here, there is shear stress here. So the only point where you won't have shear stress is going to be this point. So at this point, there won't be shear stress. Even here, there won't be shear stress. Why? Because there is no vertical line. There is no, this black line together with this blue line, they are on the same level. So there is no vertical line. So once there is no height, that means that there is no shear stress. So at this point where there is no shear stress, that means we're going to have what? We're going to have principal stress. Then the line from here to there, we're going to call it principal plane. There is no shear stress on this plane. So now the question is looking for, I'm erasing the wrong stuff. Okay, but it's fine. So the question is looking for principal stresses. Then to find the principal stress, you just have to measure from here. Always your measurements must be from the origin. You measure from the origin to where this cycle cuts this black line. So you're going to measure from here to there. So this is going to give you the principal stress. Yeah, so you can observe this with your naked eye. You can use the ruler. So the principal stress on the X phase is going to be, this is the X phase, is going to be, you will measure from here, measure from the origin, from here to there. This is the principal stress on the X phase. So you will see there it's about 34, negative 34. So it's about negative 34. Remember 35 is somewhere here. So 35 is about somewhere there. So this is 34. 34 is negative MPa. Then on this side, from here to there, you can see there, remember 30 it's somewhere here. So this is 30. Yeah, 27, 28, yeah, 29. This is 27.5. 29. Yeah, so this 29 MPa. This is stress 2. That's what we get graphically. Then when you check from analytical method, you got 28.8. When you round it, obviously it's going to be 29. You can't get 28.8 from the graph. Then on that other one, we got 34, negative 34 here. They got via calculations, we got 33.8, which is negative 34. So yeah, our answers, they are corresponding with those analytical one. They are corresponding. Right. from here, now we have to verify the angles. We have to check if you are getting the same angles. So you bring a protractor. Yeah, you check the angle of this line, this purple line here. You check the angle of this line from here to there. It's about 28.9, or we can say 29, but it's about 28.8 or 9. So this is going to be 2 theta p, 28.8 or 9 degrees Celsius. How much did we get there? We got 28.6. 28.6. 28.6. All right. They are corresponding. They are corresponding is fine. Analytically, got 28.6. Graphically, there is that one. So that is the angle from the Mohr's cycle. And as I've said, when it comes to the element, you will take that angle divided by 2, 28.89 divided by 2 for the element. Then you will get that 14 point blah blah blah. I'm just using my mind, 14.45, I think. I'm not sure. Then it means that this element will get rotated in which direction? Clockwise direction by how much? By 14 point, as I've illustrated this thing before. So 28.8 is from the Mohr's cycle. From Mohr's cycle to element, we divide that by 2. Now, why did I rotate this to clockwise direction? Why did I rotate this element to clockwise? How did I see that from the Mohr's cycle? Okay, actually what's going to happen here is that they want you to find the angle at which you must rotate this purple line to reach this black line. Remember, this is the principal plane line. This is the line, or this is the point where we're going to have the zero shear stress. This is where we're going to have the principal plane. So to move this purple line to the point of zero shear stress, it means that we have to move this line, we have to take this line, move it or rotate it from here to there. Then when you rotate this thing, you are rotating this thing in which direction? We are rotating this thing in a clockwise direction. So that clockwise is telling you what? That the angle is negative. Negative 14. So negative means clockwise. So that's why here I've rotated this element clockwise by that angle. So that clockwise direction is coming from this, from here to this black line, we will be moving clockwise. Oh, sorry, I've used the wrong side. So that angle of 14 is on the X face. As I've said, your X face will be this. But it's the same thing from here to this principal plane. Remember here the shear stress is 0. So this black line is still the principal plane. So from here to there, this movement is still clockwise. When you move like this, you're moving clockwise, which is negative angle. So from here to there, you're going to move clockwise, negative angle. Then when you measure this angle, remember this angle will be equal to this angle. Corresponding angle is equal. You will still get 28.89 here. From here to this, when you move this X face to this principal plane line, you will move it by this angle from here to there. We will get 28.89. But that is from Mohr's cycle. Then we'll take that 28.89, which is negative because of this clockwise, and then we divide it by 2, you will get this negative 14. So that 14 or 28 will go with what? Will go with the X face, as we've done it via the calculations. Then now check this angle here from this line, which is the principal plane line, to this line. This one, remember, is that one of the Y face. So to move this one to reach the principal plane, you have to rotate this thing from here up to there. Which direction is this? Is anti-clockwise. So how much is this angle from here to there? You check here. Is 0 here, 10, 20, blah, blah, yes, 90. You move like this, 150. This is 151. So the angle starting from here up to there, it's 151 degrees. 151 degrees. So to move this Y face to the principal plane, you have to move this thing in an anti-clockwise direction, which is positive. If the angle is in an anti-clockwise direction, then we're going to have the positive angle. So this angle on the motorcycle is 151. On the element is going to be 151 divided by 2. 151 divided by 2, which is 75.5. So this is that angle that goes with the Y-face. The principal stress 2. So this angle is the same angle as this one. This 151 is the same angle as this one you got from the calculations. Remember from the calculations, 2p theta equals to negative 28.6 plus 180. This negative 28.6 plus 180 equals to 151. And when you divide that 151 divided by 2, you'll get 75.7. But ourselves from the graph, we got 75.5. So it's the same thing. It's the same thing. So in that way, I think we've answered the question. We've drawn the Mohr cycle to verify the answers. So we managed to find the same answers and the same direction. So our answers are the same, and the direction is the same. So as I've said, with the angle, Here we got positive 75. Why? Because even here, when we measure from here, from this Y face, from here to there, you'll be measuring in which direction? Anti-clockwise. Anti-clockwise means positive. But when you measure from here to from this X face to this line here is clockwise. So that's why on that angle of 14 we got clockwise, which is negative. That negative means clockwise. Right, I didn't cover everything, but I think I gave the basic knowledge that you need, more especially when it comes to the direction of the shear force and the shear stress and the angle. So I think that is something that you must be careful with. Uh, Maybe I'll do another problem that will cover everything. But according to these questions here, we are done. I can see that this video as well is too long. I think I should stop here. But as well, they might ask you to calculate the resultant stress. So to calculate the resultant stress, you just have to take the ruler and measure from the point of origin. Measure from here, draw a straight line. Measure from here to this blue dot. You measure from the origin. Measure from here to there. Then you will get the resultant stress. With calculations, you used to confuse these two formulas. You used to confuse these two formulas. Where is it? Mm, oh, oh, it's this one. Yeah, so sometimes on this they will write R equals to R. So this R that you will see here stands for radius. Is not for resultant shear stress. It's not for resultant shear stress. So be careful with that. Don't use this to calculate the resultant stress. This one formula is for calculating the maximum shear stress, which will be equal to the radius of the cycle. So the formula for resultant shear stress is just that they don't write it on a formula sheet. But for resultant shear stress, resultant stress, the formula is this one. Yeah, but I will explain this one more in the next lesson. But don't confuse these two formulas. I think I'm done. Thank you very much.